Hey everyone, welcome! Today we're going to tackle a really important reaction in organic chemistry. It's called the Michael addition. You can kind of think of it as one of the most basic, fundamental tools that chemists have for snapping smaller molecules together to build up bigger, more complicated ones.
So let's start with one of the biggest questions in all of organic chemistry, right? How in the world do we actually connect carbon atoms to each other? I mean, you can picture them like little chemical Lego bricks. The whole game is figuring out how to snap them together perfectly to build something new and bigger.
And the answer, well, it's pretty simple on the surface. We do it by making new carbon-carbon bonds. I mean, forming that CC bond, that's really the heart and soul of making molecules. To get this done, chemists have come up with this entire toolbox, filled with special named reactions. And today, we're going to pull out one of the most powerful tools in that whole box.
Okay, let's dive right in. We're about to check out one of the most reliable and honestly, one of the most flexible ways to make these supercritical carbon-carbon bonds.
So here it is, the Michael addition. And if you boil it all down, it's just a way to make a new carbon-carbon bond. That's it. It's kind of like a puzzle that has two key pieces. One piece is called a nucleophile, and the other is this thing called an alpha-beta-unsaturated carbonyl compound. A bit of a mouthful, I know. But when these two specific pieces connect, bam, a new bond is formed.
All right, so let's properly meet the two main characters in this story, the two key players in this reaction. We call them the Michael donor and the Michael acceptor.
Okay, take a look here. On the left, you've got the Michael donors. These guys are loaded with electrons, they're electron-rich, so for our purposes, let's just think of them as the attacker. Then over on the right, you have the Michael acceptors. These are the opposite. They're electron-poor, they're hungry for electrons, so naturally they become our target. It's pretty straightforward. The donor attacks, and the acceptor, well, it accepts.
All right, let's focus on the Michael donor first. The most important thing about it is something called an active CH group. Now, what does that mean? It's actually simple. It just means the hydrogen, the proton on that carbon, can be plucked off really easily by a base. And as soon as that proton is gone, what's left behind? The carbon now has a negative charge, and that makes it a super powerful bond-seeking attacker, what we call a nucleophile. Okay, now for our target, the Michael acceptor. This is an alpha-beta-unsaturated compound. See that letter W on the diagram? That stands for an electron withdrawing group, something like a carbonyl. And its job is to pull electron density towards itself, right away from that double bond. And what that does is it makes the beta carbon, the one further away, really electron poor. And that creates the perfect bullseye for our donor to attack.
So, you might be wondering, how does this all actually happen? Let's get into the nitty-gritty, the mechanism. We're going to break it down into just 3 simple, easy-to-follow steps. It's a lot more straightforward than it sounds, I promise.
Okay, step 1, we have to activate the donor. As you can see here, a base just swoops in and plucks off that active proton from our Michael donor. The second that proton is gone, the carbon is left with a negative charge, and we form something called a carbanion. So now our attacker is officially armed and ready to go.
And here we go, step 2. This is the main event, the CC attack. That carbanion we just made, it goes right ahead and attacks the electron-poor beta carbon on our Michael acceptor. And in that instant, boom, a brand new carbon-carbon single bond is made. This right here, this is the whole point of the reaction. It's the most critical step.
And finally, step 3 is all about finishing the job. The messy intermediate we formed after the attack, it just needs to stabilize itself. So it grabs a proton from the surrounding solvent, a step we call protonation. This gives us our final, nice and stable product, which has a special name, the Michael adduct. And just like that, the Michael addition is complete. Done.
Awesome. So now that we've got a good handle on the Michael addition, let's take things to the next level. Let's see how it's used as the first step in an even more powerful reaction called the Robinson annulation. In this case, the Michael addition is basically the opening act that perfectly sets the stage for the main event.
Yeah, you can really think of the Robinson annulation as a combo move in chemistry. It's not just one reaction, it's a sequence of 2. The first punch, of course, is the Michael addition we just learned, and that's immediately followed by a second reaction called an intramolecular aldol condensation. When you put them together, they create an incredibly useful transformation.
So let's trace the whole process right here on the screen. Look closely.
It starts with our Michael addition, right? That forms the first new CC bond and gives us an intermediate product. Now, here's the cool part. That product doesn't just sit there. It immediately undergoes an aldol condensation within itself, inside the same molecule. This forms a second carbon-carbon bond, kicks out a water molecule, and snaps everything together to form a ring.
So you might be wondering about that word annulation in the name. What does that even mean? It's super simple. Annulation just means to build a new ring. And that's exactly what happens here. By the end of it all, we've got ourselves a brand new 6-membered ring.
Okay, so we've seen some reactions, we've seen how to build rings, which is cool, but you might be thinking, so what? Why is this so important? Does any of this actually matter in the real world?
Well, just take a look at this. The Robinson annulation is a critical, key step in making really complex molecules, like steroids. You know, the things that act as hormones in our own bodies, and are also the basis for tons of important medicines. It just goes to show you that these simple, fundamental steps we just walked through, they are the actual building blocks for these massive, sometimes life-saving molecules.
All right, let's wrap this up with the key takeaways. What do you absolutely need to remember? First, the Michael addition. Its whole job is to form new carbon-carbon bonds. Second, it always involves a donor and an acceptor. Third, it's a super important first step in bigger reactions, like the Robinson annulation. And finally, all of this matters because these reactions are how we build really important molecules, like steroids.
So, today we saw how one reaction can beautifully set up the next one. It's like a chemical 1-2 punch. Which leads me to a final question for you to think about. What other powerful combo moves do you think exist out there in the huge world of organic chemistry? It's something to think about, for sure. So keep learning, stay curious, and I'll catch you in the next one.